Hi everyone, welcome to 5.3. This is quite a big topic and I hope you can understand why gases are important. Obviously, they're essential to our life, but they're also essential to everything else. Stars are made of gas, hydrogen gas is the most abundant thing in the observable universe, and more than anything else as well, they're just pretty interesting to study. This book, 5.3, is quite a big, chunky booklet. It seeks to address two things. There is what a gas does, i.e. it exerts pressure, it occupies a volume, it has a temperature, there's all of those things that we can measure about a gas. But there's also a question of what a gas actually is. And in this video today, I'm actually going to skip over the first section in the book. I'm going to look at what a gas is first, because I think it's more important. So if you're following along with the book, go to the Kinetic Theory of Gases section of the book. It's at the bottom of page 6, starts there, and then it goes on to the next page. This looks at what a gas is, and I think that that is the most important place to start before we start looking at what a gas does, because it will help us explain exactly why we get those big effects once we know exactly what is going on the microscopic scale as well. So let's start with the kinetic theory. What is a gas? Normally I would commit an entire Monday lesson of an hour to learning 5 things. What are those 5 things? They are the 5 parameters that define our model of an ideal gas. In the book, they're just bullet pointed. I would like you now to scribble out those bullet points and replace them with the numbers 1 to 5, in this order. 1. There are a large number of gas molecules in rapid random motion. That assumption tells us what a gas is. 2. The volume of those molecules is negligible compared to the total volume of the container or of that gas. That tells me that the volume of those molecules, i.e. the atoms, is really small, negligible, virtually zero, compared to the container that that gas is in. And that's a reasonable assumption, guys, because atoms are very, very small. 3. The force between molecules is negligible, except during collisions. The force between molecules is negligible, except during collisions. And actually, this is fairly realistic, because if you think about back in internal energy, we've got the kinetic energy and the potential energy. We have to overcome a lot of potential energy in order to get something into a gas. And those forces are really small if they exist at all. And so this assumption that the forces are negligible between molecules is reasonable. It leads to a really important point later in the book, that the ideal gas contains no potential energy. It only contains kinetic energy. But don't worry about it right now. Just know, number 3, that the force between molecules is negligible, except obviously when they collide. Number 4, on the subject of those collisions, each collision is perfectly elastic. Number 4, each collision is perfectly elastic. You should know what that means because you've done it already. If you don't know what it means, well, I'll tell you, but really go back and look at 3.12 mechanics and collisions. Remember, an elastic collision is one in which there is no loss of kinetic energy. There is no loss of kinetic energy in these collisions, and it's fairly accurate to assume this, because on a microscopic level, where else would that energy go? You can't heat up an atom. That's not what heat is. Heat is the movement of atoms. So there's no heat losses. There's no heat and sound. The collisions are elastic. Number 4, collisions between molecules are perfectly elastic. The final assumption is that the time taken to collide is negligible compared to the time between collisions. The time during a collision is negligible compared to the time between collisions, i.e. the collisions take place straight away, there's no time lag, they are perfect collisions as you would see in the 3.12 book. They happen instantly and there is no time lag there. So I'll repeat them again in order. in the order that I would like you to write them down in the book as well. Number 1, what is a gas? Gas is many molecules in rapid random motion. Number 2, that the volume of each gas molecule is negligible, virtually zero, compared to the size of its container. Number 3 is that the force that those molecules feel is negligible, virtually zero, except obviously when they collide. Those collisions need to take place, otherwise it doesn't work. Number 4 is that those collisions are perfectly elastic. Those are all collisions between the molecules and between the container walls, perfectly elastic. And number 5 is that the time taken for a collision is negligible compared to the time between collisions. What you've just heard would normally be the entire lesson on Monday, a whole hour. What would I normally do? I would be getting you to commit those to memory, because those are so important. I'm willing to spend an entire day looking at those. How can you learn them now? Well, I would like you to commit some of this afternoon, up to an hour, learning them. Try making flashcards and getting your family to quiz them. Try using something like Memorise if you want to use an app. I sometimes write them in a different order, it doesn't matter. What matters is that you get the wording exactly right. So there's many molecules in rapid random motion, and the volume of those molecules is negligible compared to the container, and they feel no forces except when they collide. The collisions are perfectly elastic, and the time taken to collide is virtually zero compared to the time between collisions. It takes a bit of time. Learning things by rote is effort. Honestly, these standard answers, the reason why they're there is because they come up year on year on year. One of them will. Maybe it'll be the assumptions, maybe it'll be why it exerts a pressure. But if you learn them, you can 100% get the marks. And these are the places where people that don't bother, people that don't have the discipline to learn standard answers, always lose marks. We're literally giving you the answer and telling you to learn it. But these are essential marks, guys. Hopefully you'll see why as we go through the book. Let's just have a look at some of the implications of this model. So we know that gases exert a pressure on the wall of their container. Now, if you try and squash a balloon, you can feel it pushing back against you. That's why it's hard to pop a balloon sometimes. Thinking about collisions, a molecule, mass m, moving at speed u, will, if it hits the container wall perfectly at right angles, its momentum change there will be 2mu, because it's going mu forward and then it's going mu backwards. So its momentum there is mu, it then slows to zero in a negligible time, and then it goes back the other way. Its momentum change is 2mu because the direction has changed. Number one error people make is that they say it's zero. You silly thing. Force is proportional to the change in momentum, so it can't be zero, otherwise our gas would not exert any force. But it does. If you can't remember that, go back to doing collisions in 312, so you'll very quickly remember. I'm going to mention again Newton's second law, because that's really important here. Remember that Newton's second law is not F equals ma. Newton's second law states that force exerted on an object is proportional to its rate of change of momentum. You might also want to remember Newton's third law, that if object A exerts a force on object B exerts an equal and opposite force on object A. Those laws are really important now, because looking at the microscopic ideal gas, looking at this really molecule at a time approach, we need to understand things like, well, how does a gas actually exert pressure? If we're asked why gases exert pressure, we say this. We remind the examiner that we have done mechanics and we know what we're talking about. When a molecule collides with the wall, its momentum changes. We then also remind the examiner that in order to change the momentum of that molecule, it must have experienced a force. And in this case, the force will have come from the wall. So in order to change its momentum, the wall must have provided a force which acted on the molecule to produce the rate of change of momentum, because Newton's second law says that. If the wall has exerted a force on the gas molecule, then by Newton's third law, that molecule must have exerted an equal but opposite direction force on the wall. You cannot have force without an equal and opposite reaction force. It would not work. So by Newton's third law, if the wall is exerting a force on that molecule must be exerting a force on the wall in return. This takes place over the entire area of the container. There are gas molecules impacting on every available surface. The total pressure that the wall feels will be simply equal to the force summed up over all of the collisions divided by the area. So we just find the force exerted by every single collision that's going on and we divide it by the area. It's just showing the examiner that that's why the force is exerted. This collision takes place a lot of times over that area because there's many molecules. So force divided by area is simply a pressure. If you're really hot on your mechanics, which I'll admit you might not be right now because you've not had your progression exams to revise, maybe feeling a little bit rusty on it, it's the way it is, it's what we've got to deal with right now. Just read over a bit of collisions and a bit of Newton's laws right at the end of mechanics. Again, just check the standard answers there and you'll see that there's a lot of crossover here. This is how Unit 5 works. It's drawing on the physics that you know from other places in the course and using it here. Once you can remember your mechanics, that standard answer is lovely, it's quite easy. But you need to remember that we're talking about the microscopic scale here. And so where people sometimes get mixed up is they get the microscopic and the macroscopic mixed up. They sometimes say, because there's a volume and a temperature, there must be a pressure. That's not quite right. Whenever you're asked about why a gas exerts a pressure, you must give this microscopic description. It'll make sense to you now because I've not talked about the big scale view, but once you've done this entire book, people tend to just get the big and small confused. Try and section them off in your mind. This video has been about what an ideal gas is in terms of its assumptions and why it's able to exert things like a pressure on its container in terms of those microscopic single molecule collisions with the wall.